there we go. And we'll admit. And we got that. All righty. So, and again, this is going to work a lot like 7A did in the fact that I guess I need to change that. 7, okay, never mind. In the fact that we've already talked about hypothesis tests because um, we did that back in Unit 6, but now we're going to apply it to means versus proportions. So, and the same thing holds true for an interval as it does for a test, as it did an interval. If I happen to know my population standard deviation over here, that means I am going to conduct a z-test. So just like an interval, if I happen to know rarity, but if I happen to know my population standard deviation, then I can use a z-test, okay? However, we're going to be most of the time, we conduct a hypothesis test where the standard deviation is unknown. And when that happens, we're going to use a t instead of a z. Okay, so that means that instead of finding a z statistic, so remember a z would equal x minus x bar divided by my standard deviation is how I rolled with that as far as finding a z-score. T is going to be very similar to that, except it's going to be from a sample. So it's going to be my sample mean minus the expected mean divided by the adjustment for my standard deviation. Okay, so that is going to be what I do for a test statistic. So it's again, it's comparable. I have as far as I have an observed mean that I got from my sample, I have an expected mean that I'm going to hypothesize against. Okay, and we have my sample standard deviation. So again, it's stuff that we kind of already did, but it just looks differently. Okay. Actually, I actually will write those out. Make sure we know what all these variables are. Remember, x is going to be my sample mean. Mu is going to be my population mean. Sx is going to be the sample standard deviation. And n is going to be my sample size. So again, we're trying to, in the first example, it is just using information to find a t-value. So, and again, we have that introduction to hypothesis test. So if we are testing against a null hypothesis that my mean is equal to 31, where you get a sample data that my mean is 31.935 and my standard deviation is 2.394, my sample size was 50, find the test statistic. So this is just going through the mechanics of, we're going to find a test statistic to do this. So we're going to get t is equal to, so again, we know all this stuff up front. We know that the 31.935 was the observed sample mean. We're expecting that mean to come in at my hypothesized value of 31. We're going to divide that by 2.394 is my sample standard deviation, and we're going to divide that by the square of my sample size, which was 50. Okay, and I'll write that number down here in just a second. So let's again think about what we're talking about. We have a sampling distribution. We expect the mean of that sampling distribution to match up with my sample mean, or in this case, my hypothesized mean, excuse me. So I'm expecting that mean to come in at 31. Okay, I ended up getting a sample statistic out here, that mean of 31.935. So again, these mechanics are still exactly the same. It's a t versus a z. And so we're trying to figure out how many, in this case, instead of being how many standard deviations to the right something is, what my value of my t value, test statistic. Anyway, this turned out to be 2.76. So that means that this is 2.76 standard deviations, so to speak, t standard deviations above the mean. Okay. Now, again, that process works the same. Beforehand, if I gave you a z curve, you could look up the value in a z table. Anyway, that was lame. So we have the same exact thing true here. We're going to have a p-value that we can look up, okay, except we have to do it in a t circumstance. Okay, so once we obtain that value of t, we use a t-CDF to find the p-value. Your alternate hypothesis was being greater than 31. So again, that's why I did a poor job there. I jumped the gun. My alternate hypothesis is being greater than 31. So what happens is my calculator has oops, that's not the fastest way to my calculator. I can see all the games I play. There it is. So again, we're going to go into distribution. So shift and distribution. Okay, we're going to have a t-PDF and a t-CDF. If we scroll down there a little bit, so we see the t-CDF, which is going to be the operation that we're going to use to do that. So we're going to hit enter and get the t-CDF. Okay, my lower boundary was a 2.76. My upper boundary is going to be the infinity, so that will be, clear that out. This will be 1E99. My degrees of freedom, so we're back with that, because remember, I have a different t curve for every sample size that exists. Now, granted, as t gets larger, they morph together. But when t is relatively small, when my degrees of freedom are small, then we get something have different values there. And that didn't turn out the way it was supposed to be. Why did I say 1? Try again. Okay, that's what that turned out as 1 as well. Am I entering? I didn't even look. I'm trying to figure out why this is wrong. Lower boundary, upper boundary, degrees of freedom. Okay, I actually don't know what this calculator is doing. My TI gives me the 004 that I'm expecting for an answer, so I don't know what my calculator, I don't know what my issue is with this calculator, because obviously the area that we shaded in was not going to be 1. Okay, so this is a t-CDF. My lower boundary, again, it's going to be a lower boundary followed by an upper boundary followed by my degrees of freedom. So my lower boundary was 2.76. My upper boundary was 1E99. And I had 49 degrees of freedom, and this should get 0.004. Okay, so again, we had a p-value. My p-value is the likelihood of having a value of, so the likelihood of getting a sample of 31.9.35 or higher, given my null hypothesis is true, is 0.004, or very, very microscopic. So therefore, either one of two things have happened. My null hypothesis is wrong, or there's a grievous error somewhere. All right, and then again, we go back into our type 1 and type 2 errors. All right, now that was with again, this was, if I highlight this again, circle it again, that was with my null hypothesis, excuse me, my alternate hypothesis being greater than 31. If we go on to the next one, we talk about is not equal to 31. So do you remember how that changes things? So again, we have our t-curve. We just decided that we were out here at 2.76 and we had area above 31. We have to remember when we do the not equal to part, that means it could also be to the left of that same mark at negative 2.76. So in reality, what we do is we're going to take 2 times 0.004 for a 0.008. So we're going to double our area if we do a not equal to. If we do a two-tailed test is going to double the area. Okay, so remember, again, we're doing a hypothesis test. So after we obtain a p-value, we will make a decision. So again, that is either to reject or to fail to reject. Those are my two decisions. So again, we're going back to that. Again, the smaller the p-value, the stronger the evidence against my null hypothesis. Again, we're going back to doing comparisons. So we're going to compare p to alpha. If less than or equal to alpha, we're going to reject the null hypothesis. If it's greater than alpha, we'll fail to reject. Okay, so all of that fun stuff has remained the same. So if we were testing at an alpha level of 0.05, what conclusion would we make? Okay, so, and again, my alternate hypothesis in the first one, my alternate hypothesis was my mean was greater than 31. And since my p-value from the previous page was 0.004. Oh, and I forgot, I just want to point this out because I saw a couple people do that on their proportions test in last chapter. We always write out the word p-value because if all we did was write down p represents a population proportion. So therefore, during a hypothesis test, we have to have p-value. Okay, so I just want to make sure everybody, I mean, I don't know if I've said that before or not, but I want to make sure I did get it said because I saw several people make that mistake on their proportions test. Anyway, in this case, 0.004 is less than my significance level of 0.05, so therefore we are going to reject my null hypothesis. If we go the other direction and we talk about my alternate hypothesis of my second option, which was mean was not equal to 31, we still ended up with a p-value of 0.008, and 0.008 is less than 0.05. So again, we're going to reject my null hypothesis. Okay. Again, it's good. We have our type 1 and type 2 errors are still a thing here. Power is still a thing. So again, if my null hypothesis is true, what is the correct decision? The correct decision would be we would fail to reject it. Okay, excuse me, right. Now, if my null hypothesis is true and I rejected it, remember that is a type 1 error or alpha. If my null hypothesis is false, then the correct decision is to reject it. And that would mean if I failed to reject it, that would be my type 2 error or beta. So again, going back and refreshing our memory on all of those. As well, power is also going to be 1 minus beta. Again, that power of that test, that ability to correctly reject the null hypothesis or the probability of correctly rejecting the null hypothesis is 1 minus beta. Okay. We're going back to phantoms. So in case we need a refresher on what phantoms is, it's going to be the parameter of the problem. We're going to state our hypotheses. I'm going to pluralize. I can't pluralize hypotheses. ES, I don't know. We're moving on. Okay, so again, we're going to have a null hypothesis. And we're going to have an alternate hypothesis. Again, we're going to be using language of the mean equals some number for my null hypothesis. For my alternate hypothesis, my mean could either be greater than, it could be less than, or it could be not equal to some number. Okay, so, and make sure that we, up here in the parameter of the problem, we are going to define mean, mu. A, excuse me, stands for our assumptions. My assumptions again are going to remain the same. We have to have a random sample from population. I don't know if you guys were as slack as second hour was yesterday, but I had several people not put this. All I did was put random sample and like a checkbox or a check mark, but it has to be a random sample of my population of interest. Here, let's rewrite that. It has to be approximately normal. And again, we have the same exact three ways as far as greater than 30. Normal population, or we have the symmetric box plot. Or actually, we're going to start using dot plots. And then my last one is going to be independent. N is less than 10% of my population. Okay. Again, all of this carries over from chapter 6, so we're going to name the procedure. We're going to we're going to find a test statistic. Again, from page 1. This is going to typically be a t-value, or it's my sample mean minus the hypothesized mean divided by my sample standard deviation adjusted for my sample. We're going to obtain a p-value. Again, from page 1, we're going to obtain that p-value by using a t-CDF. We're going to make a decision. Again, that decision is based on, again, back to our language. Since our p-value is greater than or less than alpha, we will reject or fail to reject. And lastly, we're going to state a conclusion. And again, we're stating the conclusion is there is sufficient / insufficient evidence. Messy, messy, messy. To suggest that, and remember to suggest alternate hypothesis. In context, meaning we just can't say alternate hypothesis. Alrighty, here we go. Again, this is so we're going to do a one sample t-test. And so that means that my alternate hypothesis is going to be my mean is equal to some number. We already wrote this on the other page, a little bit of duplication, but that's okay. My alternate hypothesis is going to be the mean is greater than that number, the mean is less than that number, or the mean is not equal to that number. The MHS psychologist reports that the mean number of hours that students at this school sleep each night is 7. Okay, so here we have, this is going to be our hypothesized mean. After observing students falling asleep in her class, Mrs. Sapp questions that claim. She believes the true number of hours that MHS students sleep is less than 7. So again, there's going to be our alternate hypothesis. To find an estimate of the true mean, Mrs. Sapp selects a random sample, so we get to have that. Random sample of 35 students and records how many hours of sleep each hours each slept the prior night. Oh my God. The sample mean is 5.67 and with a standard deviation of 1.88. So we got this standard deviation here. We can go ahead and put the mean population mean here. The hypothesized mean is there. What else did I have here? Oh, we have n equals 35. Test the claim using a one-sided hypothesis test to use a level of significance of alpha level of 0.05. So again, this is where we're going to roll through our phantoms. Okay. So typically we would, I mean, again, it's your preference on how you do this. We could line it out with phantoms and just do it. Personally, if you're going through this, I just know I need to, and here it's a checklist thing. Because the first part is technically, I mean, to me, it's out of order. We need to establish, hey, wait a second, I'm trying to test the claim. So that means I'm going to do a hypothesis test. Okay, because I do not know the population standard deviation, that means I'm going to do a one sample t-test for means. So I have named it. Okay, that part is done. So we're going to write some hypotheses. In order to do this, I need to make sure my assumptions are true. So here are my assumptions. To do this test, I have to have a random sample of Mrs. Sapp's students, or of MHS students. What did she do? Of MHS students. Number two, will my sampling distribution be approximately normal? Is my sample size large enough? And she did. 35 is greater than 30. 3, independent. Did I lose my probability because I got my sample size too large and 35 is less than 10% of all MHS students? Okay, so my assumptions are taken care of. Okay, this is the only one on this page. We're good. Okay, now that I'm ready to do that, now I'm going to write down my hypotheses. My null hypothesis is this mean does equal 7. Mrs. Sapp's claim is that the mean is less than 7, where our mean is the true number of hours of sleep MHS students get, or something of that nature. I didn't word that very good at all. But okay, onward and upward. So what the heck? Oh, we're still on Wednesday's schedule, huh? All right. Anyway, we have stated a hypothesis. We've identified our parameter. So we are on to our test statistic. So again, now we have to be very we have to pay attention to what we're doing here because it's...
Please disregard the bell.
Really? All right then. So because what I'll see is I'll see people accidentally give me a Z here, and it's not a Z. So, or I have people that won't give me a variable at all, and I have to know that you know whether it's a Z or a T. So here we go. So we have, she got the sample mean rolling in here at 5.67 minus the observed mean, which was 7. Excuse me, I said that backwards. The observed mean is 5.67. The expected mean was 7. The standard deviation was 1.88, and we're going to divide that by the square root of 35. So remember, let's talk about what we're expecting here, okay? We are expecting here And the drawing of the curve is not necessary. It just kind of helps us picture, making sure we get this picture right. We're expecting it to be 7 in the middle. We came in at 5.67. What is the probability that it is 5.67 or less, given my null hypothesis is true? That's what we're trying to find here. So we're going to turn this into a test statistic. This test statistic is way out there. Way out there. Negative 4.19. Okay. So that is microscopic. And now we need to obtain a p-value. Oops, so we got our test statistic. We're going to get our p-value. So again, we're going to go out to our calculator and do the TCDF. However, I'm not going to go out to my calculator and do a TCDF. I'm going to go out to my calculator. And we're going to go stats. We're going to go over to tests. And we're going to do, again, we're going to do a t-test. So I'm going to select option number 2, which is a t-test. I have statistics. So we're going to go over to statistics. Again, I have my, and again, it's understanding what your calculator is wanting you. It's going mean null. So my null mean was already forgotten, 7. Okay. My sample mean came in at 5.67. My sample standard deviation, it rolled in at 1.88. My sample size, we know to be 35. Okay, now we have to know my alternate hypothesis. Which way am I testing? We are testing as less than my null hypothesis. And I'm going to calculate that. And I'm going to hit enter. Okay, so there we go. We get, there's the t statistic at negative 4.18. We had that down there earlier. And we're going to get a, wow, tiny number, 4 zeros and a 9. Now I will go back and put in the notes in here. So if we're doing this by hand, this would be a TCDF of negative infinity to a negative 4.19. And then we get a 34 degrees of freedom. And again, this is something I may have failed to do very good, I guess, in my modeling, because very, very few people were writing down degrees of freedom on what I was able to grade during for second hour. So I don't know if that's a second hour thing or whether that's just me in general and a systematic failure on my behalf, but we need to make sure we're writing down degrees of freedom. Anyway, this turns out to be 1, 2, 3, 4, 9. Okay. So actually that brings up another good point, because I'll see people do this. They'll write down a probability of 9.44. Now, number one, hopefully that raises a red flag in your brain, because we're not going to have a probability ever over 1. So to get something that says 9 either means we made a mistake or did something else. In this case, we didn't see the negative 5. Okay. Now we have obtained a p-value, so that part is taken care of. My pen stopped. All right, we're ready to make a decision. Since our p-value is less than our alpha level. Now the question is, did we write down an alpha level or did we have that given to us? In this case, we had the alpha level given to us, so we're okay. Since our p-value is less than alpha, we will reject the null hypothesis. There is sufficient evidence to suggest the mean number of hours slept is less than 7 hours. We have made a decision and we have stated a conclusion. Oh, man. Okay. I was going to jump the gun and not say jump the gun, but I was going to enter data ahead of time, so you didn't have to see me enter all of this. We may, for time's sake, we just may go off notes today. So a jeweler is planning on manufacturing gold charms. His design calls for a particular piece to contain 0.08 ounces of gold. The jeweler would like to know if the pieces that he makes contain on average 0.08 ounces of gold. To test to see if the pieces contain that amount of gold, he made a random sample of 16 for these particular pieces and obtained the following data. Use a level of significance of 0.01 to perform the hypothesis test. Okay. So this again requires us to, it tells us to perform an appropriate hypothesis test. So again, this is going to be a mean. So a mean. So when I come across a problem, I'm going to look. Okay. They tell me to do a hypothesis test. So if it's a proportion problem, that means I'm going to do a z-test. If it's a mean problem, more than likely, I'm going to use a t-test. However, if I happen to know the population standard deviation, then I will use a z-test for that. But more than likely, I'm going to use a t-test. All right, so our phantoms again. So we have decided that we're going to do a one sample t-test. So in order to do that t-test, we'll make sure our assumptions are true. Random sample of gold pieces, gold charms. That's a good question. Did we have a random sample? Oh, there it is. We did have a random sample. Number 2, is this approximately normal? This one, where's that at? Okay. So I'm going to go off my, oh my gosh, do I take time? I don't know. How long is it going to take me to enter that? Okay. This was a failure to plan on my behalf, and we'll hope I get these typed in right the first time, so I don't have to go back and find where my mistake was. So we'll be very diligent about not making errors. All right, there's my 16 pieces. I've double checked them as I was entering them, so as long as I wasn't getting too fast, too much of a hurry. Here we go. All right. I don't know why I swiped over here, because we need to see if my plot, so we're going, I got 2 of them turned on, so I'm going to go into plot number 2 and turn plot number 2 off. We're going to go back up into plot 1. Plot 1 is still turned on. It's doing a box plot. It's doing it from list 1. So I think I should be able to hit zoom stat, and I should be good to go. All right. Well, that matches up with the picture I have in the notes. So this is not looking good for the home team. We've got an outlier in there. So, and again, in reality, and I guess I'm going to start making a more emphasis on this. We could be making a dot plot, I wish my calculator won't do a dot plot. We'd have to do that by hand. In reality, what the best thing to do is look at the histogram for this. And yeah, that's what I thought would happen. We're going to get something that's huge, and then we have to do it's a lot bigger pain. Um, so yeah, moving on. Just ignore that. I mean, we should take time to do a dot plot instead. Is what we should do. Again, I'm not for sure it's going to end up ever being anything critical. But here, sorry, I'm babbling now when I shouldn't be. Okay, so we're going to copy this box plot. Okay, so it has outlier. We're going to proceed with caution. Independent. $16. We'll assume that 16 is less than 10% of all of his charms. So that means he's got to have 160 on the shelf, which I don't know. Okay, so we have nailed our assumptions. We've got a name taken care of. We need some hypotheses to go off of. Okay, so everything checks out, kinda. Approximate normal wasn't quite there, but that's okay. So my null hypothesis is that, again, it's going to be what that mean that I need is. So we want the particular gold piece to obtain to be 0.08. Again, okay, again, that came from right here. My alternate hypothesis is going to be based upon what the question asks us to do. To test to see if he takes a random sample. Let's just say the jeweler would like to know if the pieces that he makes contain 0.08 gold on average. So therefore, this is going to be a not equal to test. It's going to be a two-sided test because he's just saying, hey, is it 0.08? Is it not? Okay. And now we have to define what that is. Mean equals the true mean gold content of each charm. So with that, we have stated our hypotheses and we have done the parameter of interest. All right, now this makes it a little bit hard as far as we weren't going from summary statistics. So if I'm to write down the t value, which I do have to write it down, I would, if I'm right on the test, you're gonna have to write me out the formula. In order to do that, you're gonna have to know what the mean and the standard deviation is. So when we come back out here and run our test, so now we're gonna go stat, we're gonna go over to test, and we're doing that t-test again, number 2, except this time we're doing it from data. Okay, when we do it from data, again, it's knowing what it asked for. It's asking for my null mean. So therefore, again, I was testing this against 0.08. My data is stored in list 1. A frequency will always be 1. I had some people during this last part that were trying to put something else in there, the L1 as well, but no, my frequency list is always going to stay 1. Okay, except on this one where my test is going to be not equal to. So we're doing a two-sided test. And we're going to calculate that. Okay, now my calculator then gives, I don't have to necessarily run my one variable statistic on this, because when I run my t-test, it is going to give me my summary statistics that I'm going to write down. So I'm going to write down the mean, and I'm going to write down the standard deviation, and I'm going to write down a p-value. I'm actually all 4 of those things. Everything that's there, I'm going to end up writing down. Okay, so up here, we know that my sample mean rolled in at 0.07798. And again, decimal wise, it gets a little bit squishy because there is no standard. These are small numbers, so I'm going out a long ways with my decimal values. We know that, what else were we given? We know that n is equal to 16. My degrees of freedom is going to be 15, and we're going to test against an alpha level of 0.01. Okay, so that's all the other things that we would need out of this. So to obtain my test statistic, the observed mean gold amount is 0.7798. First glance, I'm saying he's hurting. I'm expecting a 0.08. Okay, so he's a little bit below that. Because my standard deviation is 0.025, but then I have to divide it by the square root of 16. Okay, so this goes back to what did my calculator output for a t statistic? I would never ever actually do this I would never do that hand calculation. I just want you guys to be able to tell me. And again, the diagram is not part of what's required on an AP answer. It's actually not required on mine, but for notes wise, again, it helps us. I'm just understanding this is a two-tailed test because it's not equal to. That means back here at 3.21 and up here at positive 3.21, and I'm going to go the area both ways because it ended up giving me a p-value of 0.0058. And just as a reminder, we're going to do this as well. So this was doing a TCDF of negative 1E99, negative 3.21, and 15 degrees of freedom, gives us a 0.0029. But I got a 0.058 over here, so what I had to remember, this was a two-tailed test, so we have to take it times 2. Okay, so just a reminder of what that is. We have a test statistic, we obtained a p-value, we're ready to make a decision. Again, since our p-value is less than alpha, we will reject HO. There is sufficient evidence to suggest the mean amount of gold is not 0.08 ounces. And actually, going back to this, again, this is one of those things of there's so many details that we need to really pay attention to. My definition of my mean is weak because I should have put true mean gold content in ounces is a much better. And that way, if I do it up there, if I forget to put it down here, I'm okay. I've got that ounces out there. I got that defined somewhere. Okay, what do we got left? 2. I don't know if we'll get 2 in. We'll try to get 2 in. Okay. Moving on to what's called a matched pairs t-test. Okay, so what happens in a matched pairs t-test is we're going to take one sample. We're going to, for example, if I did something with my right hand versus my left hand, if I wanted to take the time it took me to stack, let's go back to the cup stacking activities. If I was stacking with my right hand versus stacking with my left hand, would there be a difference in time? That was one sample. That would be me. I would take my time with my left, my time with my right. I would subtract those two and give me that. So therefore, if the null hypothesis would always be that then we would do the difference between those two, and that difference would turn out to be 0. My alternate hypothesis would be the mean difference is going to be greater than 0. It could be less than 0, or it could be not equal to 0, depending on what I'm testing. Okay. So again, the difference is going to be the difference between the treatments in context. And also remember, this could end up having random assignment. So be paying attention to that. So let's see what we have here. Suppose we're interested in the symptoms of caffeine withdrawal. We want to study whether individuals deprived of caffeine exhibit more headaches. We recruit 10 individuals willing to participate in our experiment. Each subject was barred from consuming coffee, cola, or other substances containing caffeine for the duration of our experiment. During one 2-day period, subjects took capsules containing their usual caffeine intake. During another 2-day period, the subject received placebo pills. We randomized the order in which the subject took pills. At the end of the day, we had the subjects who recorded their headache level from a 0 to a 10. So this is the first individual. Okay, I don't know why I did that. How did I draw? See, I don't understand. How did I draw a perfect circle? Sorry, I digress. So we are going with the difference between the two. So that would be a -1 because we're going to do the difference between, so we're doing caffeine minus placebo. So if we look at the difference from all those, so individual number 3 has a -4. Individual 4 is a -5. See, -1. Okay, 0, a -2, -3, -2, 0, and -1. So what happens is I need to drop these into a new list. I'm going to put those in list 2 in the calculator. Okay, and the thing is, the matched pairs t-test that we're doing right now is no different than the previous test as far as the test process. The only difference is how we're setting it up. I'm taking one individual in one 2-day time frame. I'm not giving them caffeine. In another 2-day period, I'm giving them caffeine, and we're going to take the difference between the two headache levels between the 2 days, and we're going to see, does caffeine withdrawal cause headaches to some extent. Okay, so that's what we're going to do here. All right, so again, because we have the same individuals getting both treatments, this is a matched pairs t-test. In order to do the test, we have to make sure our assumptions are true. Random assignment of treatments. That was just the randomized order. Approximately normal. We would go create a box plot. For time's sake, this is horrible. Not symmetric, so we're going to proceed with caution. Independent is not needed for experiment. So if you didn't write it down, we're good. All right, again, this is where the phantoms is the checklist. Hopefully we're just getting down the process. We have named it. We have done our assumptions. We have a null hypothesis. Now, the null hypothesis means if caffeine has no effect on it, we should not see a difference in my headache level. So that means my mean difference is going to be 0. So that's what I'm testing against. I think, and again, here's where you have to pay attention to what is it at. It's saying, what's it say? We want to study whether individuals have more headaches or their headache is more severe. Okay. Actually, I should read their headache is more severe because we're rating the headache. But we went with caffeine minus placebo. So if we're saying that caffeine is, what are we saying? Because I have less than 0. Why would it be less than 0? Sorry, I'm rereading the question. Huh. Okay, they recorded their headache level. I don't know. I'm questioning what I have here. Why would this be negative? This would indicate Okay. This question actually isn't very clear on which way we need to go here. It just says more headaches. It actually says nothing about the level of the headache. So we're going to assume that people that are able to have their caffeine have less severe headaches. So because they have less severe headaches, I should end up with a negative number over here. Okay. So we're going to deal with that. Okay. So we have to define what that is, though that mean difference is the mean difference of headache rating of people like those in study when having caffeine and not. Placebo pills. Okay. Whew. Killing my time now. Anyway, so now we need to test statistics. So again, if we go out to my calculator to do this, hopefully it didn't take too long to drop a list in there. So I'll go over here to L2 and clear that out. And type these in real fast. So we have a -1, a 0, a -4, and a -1, and a 0, and a -2. All right, something's amiss. -1, 0, -4, -1. Well, so we're in the same order. I missed a 0. -2, -3, -2, 0, -1. Okay. I'm in cell 11, so that means I have 10. So, okay, we're good. Okay. Again, if we want to go back and see that dot plot or that box plot, I'll go back and show that to you real fast. So again, we're going to clear that out and we're going to put L2 in there and we're going to zoom stat. And so, oh, I still have that on the box plot. So we can clearly see that box plot is skewed left. All right. So again, we knew that from the shape of our box plot. So anyway, man, I feel like I'm making a mess of this today. Okay. And it didn't even show. No, I didn't have the outlier. So there's our ugly looking box plot. Anyway, that's not what I was even after. For stats, we're going to go over to test and what test we're going to do. So again, even though this is a matched pairs t-test, this is matched pairs is just indicating the style of what I did up front. So that's why we had to go with matched pairs. Okay. So after the matched pairs, so we actually have data from this. So my null hypothesis, we're comparing this against a mean of 0. My data is stored in list 2. And again, we were testing to be, we think the caffeine is lessening the severity of the headache. So we're going to hit enter. And so there we have what I need to have written down. It's just, again, I like to have the mean, the standard deviation, and all that fun stuff written down. We'll go ahead and slip all that fun stuff down. So over here, we ended up with a mean of -1.4. We had a standard deviation of a 1.35. We had a sample size of 10, which means we have a degree of freedom of 9. And we were testing. Did it tell me what I'm testing against? It did not. So we're going to do a standard 0.05. Okay. So my test statistic is going to be observed difference is -1.04. Again, I like to have the 0 in there. I noticed that some of you didn't like to write down the 0 because it makes never mind for the value of my numerator, but that's what it is. Anyway, we have the square root of 10. And that's going to give me a -3.28. Okay, so once again, if I have a curve here, we're sitting down here at a -3.28. So there's not going to be much area to this. Okay, the p-value the p-value from my calculator output was a 0.048. And again, we're going to be, we're just rejecting family today. We have a test statistic. We've obtained a p-value. We're getting ready to make a decision. Since our p-value is less than alpha, we will reject the null hypothesis. There is sufficient evidence to suggest that people like those in the study will have less severe headaches when consuming caffeine. Okay. Very rarely do I put us over the hour mark. However, I am today just because I want to get the other one, the mass pairs t-test that's in our notes here, taken care of. Because then on Monday we need to take care of the 2 sample stuff so we can kind of get that done for the week. I'm going to, I didn't say rush through that, but we're going to move through this pretty fast. I probably won't take time to enter this in my calculator. And maybe this should have been a day we started before 8 o'clock, but. So in this one, we are determining the difference between the length. We want to compare a Titleist and a Callaway. You want to show that the Titleist hits further than Callaway. So that's important because that's going to establish what direction my alternate hypothesis goes. Okay. Titleist hits further than Callaway. By comparing 10 random pairs, 1 Titleist and 1 Callaway of the same type. Each pair is hit by the same randomly chosen professional golfer. So again, this has a lot of assumptions in it. We're going to assume that professional golfer is very consistent about how he hits his golf ball. Measurements and the number of yards are recorded below. Is this sufficient evidence that Titleist hits further than Callaway? Okay, so again, we would drop that into a list in our calculator and we're going to see, does that difference, what we're going to do. Okay, so again, because we have the 1 sample, we have the 10 golfers. The 10 golfers swung a Titleist club and then swung a Callaway club. So that means that this is going to be a matched pairs t-test. Okay, 1 sample. 1 set of sample, or one set of individuals, 2 different samples or 2 different outcomes because of each treatment. And then we move on. Okay, so again, we're going to go with a matched pairs t-test, and we're going with Titleist minus Callaway. All right, in order to do this, we'll have to make sure that our assumptions are there. Random selection, a professional golfer. To make this better, we should have been randomly, were they randomly assigned, did they hit Titleist first and then Callaway, or were they, did they know which club they were swinging? Because that makes a difference too. If it, maybe if they didn't, they wanted to swing the Callaway harder or better because they wanted that to win, the things like that. So this is a case where we'd have to blind them somehow, that they didn't know which club they were swinging. But we had the random selection of a professional golfer. Okay. Number 2 is, this is approximately normal. If we would have the time and we would take a look at that box plot, it is roughly symmetric. And again, this is an experiment, so we did not necessarily need independency. So again, we'll keep doing our checklist. Just make sure we keep everything intact. We've done a name, we've done our assumptions. We're ready to do some hypotheses. My null hypothesis, again, because this is a matched pairs t-test, we're going to assume the difference was going to be 0. Now, here's where we have to pay attention to which way we subtracted this. Again, for which way the order matters. The other one kind of got botched because it didn't just come out and say that we're trying to see if headaches are reduced by caffeine. This one does. It wants to know, does Titleist hit further than Callaway? So if I'm going Titleist minus Callaway, excuse me, that difference is going to have to be greater than 0. Was this in yards? Yes, number of yards. Mean yards, the golf ball goes when hit by professional golfer. Okay, so scrolling down here, we have a hypothesized, we have identified our parameter of interest. So again, we're going to go out to our calculator. If we did our calculator, we'd find out the mean of this is going to be 1.44. The standard deviation of this is going to be 6.085. We have a sample size, even though, okay, so I think our problem was we have 10 up here, but we only have 9 down here, so it is 9. Okay, so my degrees of freedom is going to be 8, and then my alpha level is 0.05. So again, my t statistic, I observed a mean of 1.44. I'm expecting a mean of 0, and we get 6.085 divided by the square root of 9. And that gives me 0.712. All right. 0.248. So again, just to help us out, we're expecting it to come in here. We're expecting it to come in at 0. We got it to come in at 1.44, which gives me a t is equal to 0.712. So that means that the area of this is going to be 0.2418. How about just a 248? Okay, that's what we got going on here. So again, the p-value is the probability of getting this outcome given my null hypothesis is true. So this is going to be not rare at all. So therefore, I'm going to assume that my null hypothesis is true. Since the p-value is greater than alpha, we will fail to reject our null hypothesis. There is insufficient evidence to suggest Titleist clubs hit further than Callaway. Okay. That wasn't too horribly long. So for those of us that are struggling to get that written down, I will kill time here for a little bit. I am going to, though, stop the recording.